Me, Funny as a bone. This is my Physics 2212 Lab 3. The purpose of this lab is to measure the distance-dependent magnetic field of a small bar magnet, then compare the observed versus predicted distances on the on and off axis magnetic fields. And in my results, I found n to be negative 2.673, and my magnetic dipole moment, I calculated it to be this number. Some physics principles that we used in this lab were the Savart law, the magnetic field of a dipole, which was given to us in the lab instructions, and the distance dependence formula. So our experiment steps include we oriented the phone to make the magnetometer perpendicular to the magnetic field of the Earth. Then we found the location of the magnetometer chip on the phone. And then finally we measured the distance between the magnetometer and the bar magnets on the on and off axis. So to the left, you'll see that we have our distances paired with our magnetic field strengths of the magnet. And then to the right, we have we plotted these values. And if you see the x, or the slope of this line is actually our n value. This is from our distance dependence formula. You can also find k if you take because the second part is ln of k, so if you take the e of this, we found k to be, I believe it was, this is our data for the off-axis field, and all the data are shown in the table. So for some calculations, we know that n is our slope of the graph, and our y-intercept, we took the e of the y-intercept to get rid of the ln, and then we are left with 0.7649077781. That's what I found to my k. Using that k and n, and also well, k and n we used to solve for our r magnitude, which we used to plug into our rearranged equation here to find the mute mag, which I found to be this number. And then using that data, I plugged it into my code. So for my code, you can see I plugged in the mute magnitude into our code. And then we created our dipole function. You can see we plugged in our formula here for the magnetic field of a dipole. And then create our scale. Um, and then we basically just creating our arrows to represent the magnetic fields on and off axis. And finally we print out our function. This is what I got. Um, the orange arrows represent the magnetic field that's on axis, while the blue represents the ones that are perpendicular to the axis, and the purple represents the 45-degree magnetic field. So some possible sources of error are the inaccuracy of the magnetometer. So some of the readings can be inaccurate. Inconsistency with phone angling. So sometimes we didn't angle the phone as accurately as we wanted to. Other outside system magnetic fields and averages. So a lot of the data we used were averages of like multiple trials. So and one particular one I saw was in the NRR vector. The average I found was different from the one that I calculated, so that could throw off some data. Some of the observations I made were that I found the first and the fourth one to be true, because they just accurately described the distance dependency formula, while the 2 and 3 didn't. So these are my answers for the observations. Now for our what if and why. What if you hadn't oriented your experiment to compensate for magnetic north, and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? The measured magnetic fields would be different as the magnetic north wouldn't only affect the y component but also the x component, causing both components to be different. This would significantly alter our results. And then for the what if you were to stick two identical magnets together end to end and run the experiment again, how would you expect your measurements to differ? Well, due to superposition, the net magnetic field magnitude would increase. This would lead to our distance measurements to be greater. And that's it.